Okay, so this week we're going to look at the z-transform property. All right, so I think it's pretty straightforward, so I probably just quickly go through my solution. Here, if we want to prove that this one is true, so what we do is we first find out the expression for yn, and then we do a z-transform. And then that's the left hand side. For the right hand side, we do z-transform for these two. Okay, so we can prove, if we can find the left hand side and the right hand side is a match, then it's good. Okay, so for the left hand side, so the expression for yn is you just put the xn into it. So xn's look like this. So xn minus 1 is another term, so you just put it in, and this is the result, and this is the xn minus 1. Okay, so then you do a z-transform of that one. The only thing you want to pay attention is the time delay is in the z domain is z to the order of -1. Okay, that's the only difference. And we can collect terms. We got this form. Okay, for the right hand side, we do y1 and y2 individually. So for y1, we do this one. Again, we got this part. And for y2, we got this part for the time delay. Okay, and if we compare them, so you can see we got this part here. This is the right hand side. We got this part as well. And there's A1, so we put A1 in front of a Y1. So we put A1 here. That's exactly the match. Okay. Same thing for Y2. That's first question. Okay. Second question is also pretty simple. So we want to prove this one. So you can just do a z-transform for this one. That's the definition. If you want to do a z-transform, you just put the targeted signal here, and so we only count for n larger than 0, and we put this z to the order -n to the end, and we sum all the term. Okay, so now we just put the target signal in. Okay, and we're gonna replace this n minus L with a new letter K. All right, so everything is about K, and this n equals to K plus L, so negative that. And this term can be split into two parts, this one here and here. Okay, and all these things, and you can see this UK becomes 0 here. Okay, so all this one is the definition of the transform. So this red box becomes this capital Z, this is Z transform, and what left is this one. Okay, it's proved in time domain delay. You just put a Z to the order -L to multiply with the original Z transform. Okay, so part 3, let me bring this down. Part 3 is also not very complicated. So question 3 is talking about an impulse response is defined as that. Does the system represent a causal system? First, you want to understand what is impulse response. Okay, impulse. So for any system, if you give a signal as input, you will see a response. For arbitrary signal, you're going to see arbitrary response. But if your input signal is impulse signal, okay, we talked about this before, and that response have a special name called impulse response, and it have a special letter H reserved for this response. So Hn is always being impulse response. Okay, so that's impulse response. And what is causal system? So if you have a like inputs or step change at time 2, all the response only happened after that time, so after t equal to 2. There's nothing before that because there's no, stimulus or, trigger in the system, right? So that's called a causal system. This is a causal system. Okay? So if otherwise, if this haven't happened yet, but there is something happened, so this is a non-causal, okay? Non-causal. So in reality, all this physical system is a causal system. So in this one, if we look at this one, how can we tell? So we see that if you have an impulse response, which is t equal to 0, and you're gonna have a response look like this. Because of this term, everything happened after t equal to 0. Okay, so there is nothing before t equal to 0, so it's a causal system. All right, so we can tell by looking at this expression. And next one is this system BIBO, bounded in and bounded out. Okay, so if you give a system an input signal, if it's a bounded, it's not like go infinite, it's have a boundary. Okay, it's not an infinite signal. If that's bounded in, we are looking for a bounded out. So this is a BIBO. Okay, not so the result is not go crazy. It will be decay or be constant. So this kind of a signal called a BI. This is a system called a BIBO, or we call it stable. We want a stable system, right? So you give a regular signal, you expecting the system give you a stable response or a decaying response. All right. So mathematically speaking, so this HK again is the impulse response. Okay, so if you gave a impulse response to the system, and if your response is less than infinite, okay, if you sum all the response, then we will say this is stable. Okay, this is definition, and we just look at if this one is stable or not. So this is from the question. Okay, this one from the question. Okay, and that's the response. If we collect the response from k equal to 0, because there is a unit step function, then we got this power series, and you can see that's the sum of the series. It converge or less than 0. The sum is less than 0, called converge, only when a absolute a is smaller than 1. Okay, so if a is smaller than 1, then this one is a 0, right? So it goes like infinite. Then you have a finite sum. Otherwise, it just go infinite. All right. So for question 4, we want to prove that the convolution in time domain equals to production or multiplication in Z domain. Okay, we have similar property for Laplace transform, for Fourier transform. We want to prove that again. So left hand side is this one, xn convolute with hn, and this is the convolution definition. All right, so you put hn to hk, change a variable, and another one is n minus k. Okay, you flip and shift, so that's and you multiply and add all those product together. That's a definition for convolution. And we want to do a Z transform. To do a Z transform, you can see the blue thing is we just put the target signal or function inside of this sum and Z to the order of negative n. That's the definition for Z transform. Again, we're going to substitute n minus k, use a different letter. Okay, and this k is still k, n minus k become L, and n become L plus k, so there's no n anymore. Okay, and this term can be split into two terms. Okay, so what we got so far is we got a 2 sum sign, we got something in between, and we got a 2z kind of term, z power term. Okay, and then we're going to regroup it. We take one sum sign here, we take one term x here, and we take a z here, and I'm going to regroup this one, put this one here, and we got a k here, and we got the left z down here. Okay, and if you look at this one, that's the definition for z transform of lowercase l, okay, become capital case z, and this lowercase h become capital HZ. Okay, the definition for z transform, and you just multiply them together. Very last one. So if you want to determine the capital H e to the order of j omega, so the step is you want to find you use HN to do a z transform, and this plug in or replace z with e to the order of j omega. You got h of e to the order of j omega, and then you find the magnitude of that one. So you got that one. Okay, you find the magnitude. So first, I just copy down the HN expression and do a z transform, and this is the equation we're going to use. The z transform of a delta function is 1. Okay, so this become 1. This is 1 multiplied with z to the order of -1. Again, time shift. Okay, we proved that. That's the time shift, and this is time shift for 2 units. Okay, and then we just replace z with e to the order of j omega. That's the same. So z become e to the order of j omega to the order of -1. This is to the order of -2. Okay, and what's next? We just bring this one in, because you can do that for exponential function, and this one in as well, so it's on the shoulder of e. And then we're going to take e to the order of -omega out. So this was a constant. You take this thing out, take a negative j omega, then what you left is a positive j omega. So they multiply each other equal to a 1. Okay, and there was a e to the order of -j omega become a 1, and there are 2 of them. You take one, is 1 left. Okay, and you bring 1 at the front and bring 1/2 at the outside of the brackets. You got this one. Okay, and that is the definition of that's the Euler equation for cosine omega. Okay, and we got one extra thing at here. Okay, and the magnitude of this part is 1, and the magnitude of this part we can just copy down here. So that's the magnitude of 1 plus omega cosine omega. Okay, so that's a very quick go through of this week's tutorial.